Yes, thank you very much. And first of all, I would like to thank the organizers for inviting me here, and also for all of you to coming here. So first of all, it will be a different talk from those that you have seen so far. So before you heard about learning, deep learning, in this talk, I will be trying to tell you something that can be used for learning, can be used by modern learning algorithms. So my talk will be really about some foundations of a new area, I believe, in algorithms, which is getting bigger and bigger importance because of its implication, among others, to machine learning. But in this talk, I will be talking more about foundations of the area. So I don't know how many of you have been studying computer science, but in undergraduate curriculum, normally since 70s, the main focus of computational complexity, classical computational complexity, was, okay, to distinguish what is the to say what is the complexity of the problem, and then optimally to say, oh, this problem we can solve in polynomial time, or another problem is hard, is, for example, NP hard. However, in modern times, we have to think about something different. So increasing role of computers, of networks, of data, increasing size of data, forces us to think about different way of approaching the complexity of specific problems. So, you know, this is a map of massive data, let's say a decade or 2 decades ago. Right now, if we're talking about big data, this is a big network. Data, this is a, you know, there are many applications of big networks, big data, which are having sizes of millions, billions, or even trillions of objects. So modern data are really huge, and we have to think about other way of approaching it. So, you know, if right now we have a data of size 2 to 15, the question of how to process this is different from the classical questions that people have been studying in computer science. So, modern data science observes big network everywhere, and this is what I would like to think in this talk about. So here are some examples, you know, social network, World Wide Web, cost citation graphs. And the size of these graphs are big. And I believe that, you know, big companies like Google and Yandex are trying to analyze it. But actually, even we on our laptops would like to process this data. So when we have such big data, we have to, as I said, rethink the concept of complexity of problems. So our goal is not just to analyze this data, but we would like to really analyze it quickly, efficiently, to be able to extract important information in the time which we can afford to spend. And with that, one of the central problems that we see nowadays is the concept of sublinear algorithms. In short, it means we want to study some problems, analyzing data, and would like to do it in sublinear time or sublinear space. Sublinear with respect to the input size. So if our input is a graph with 10 to 15 nodes, we would like to say something about this graph faster than by processing all the nodes and all the links in the network. So now a few things about how to achieve sublinear time. So as you have seen, as I said, we cannot really read the entire input. And because of that, some problems are trivially hard. So for example, you know, if you have an input, and if you want to check if one of these numbers in the input, you have input of size 10 to 12, 10 to 20, and you want to check if one number is even or not, you cannot really do it in the worst case faster by just going through the entire input. However, some problems are easy. And, you know, the most natural, the most standard thing is, you know, election forecast. But we have seen lots of other applications. Now, one thing about real challenges of studying this type of problems, we also see every day. So I don't know how many of you have been studying in detail election results in the UK. So in England, in the United Kingdom, in April, there were elections. And there was a quite clear prediction what will happen. And it was clear for many, I mean, in all the forecasts, we are assuming that there will be some hang parliament, that, you know, the leading party, they will not have majority, and they will be pretty close call. At the end, one party got more over 50%. So even nowadays, and so this was all the polls were saying essentially the same, that we'll have hang parliament. And the reality was that, you know, one party got 10% more than expected, and another party got 10% less than expected. So even in nowadays, we see these examples, the most natural examples, that, you know, classical tools are failing. So, because we cannot read the whole input, we have to make some sacrifices. We'll get approximate solutions, and we'll have to, in most of the cases, we'll be using randomization. Now, in this talk, I'll be focusing on, so I will try to give you the feeling, the flavor of the subject, and I will be skipping many equally important, interesting areas of sublinear algorithms, or the ways how we can approach this task. So one, the most natural, which many, for example, many companies are using, is that first you process data. So you have some big graph, so why you don't want to first collect all possible information about this graph, and then you will be able to have very quick responses. I want to study kind of fundamental question. Suppose we don't have the comfort of doing it. Suppose all what we have is we have input, what can we say about this input? As quickly as possible. So now, as many of you have seen, the most standard approach to achieve something like that is to do sampling. So normally, many algorithms will be using just random sampling, but actually, really interesting algorithms will be using some adaptive sampling, and will run some stochastic process behind the scene to be able to obtain more information in some right way that will give us better results. So what is the plan of the talk? I want to show you some examples, and I want to focus only on problems on networks, on graphs. They are quite representative, but again, it's just small snapshot of what's going on in this area. And our main goal will be to think really about analyzing performance of these algorithms rigorously. So what I'm saying by that, I would like to say, okay, what is the running time that I can predict? Okay, this will be the running time, and to some extent, I can make you a promise. This will be the running time of this algorithm, rigorously. Then, what is the approximation ratio? As I said, we'll have approximation algorithms. For example, they will have 1% error. So I want to have strict bound for error. And the next thing is I also want to make sure that I understand error bounds, though in this talk, I will kind of ignore the last issue. But these are three important issues which are important. Now, comparing to most of the talks in this workshop, this talk will be about algorithms and complexity of the problems. And this will be sample problems, fundamental problems. And the main issue here will be how to rigorously study the problems. And I will just give you only examples without many details, but hopefully you will get the main ideas. OK, so let's start with maybe the most natural, the simplest problem in graphs. So suppose that I have a graph, and I want to say what is the average degree, or if you prefer, what is the number of edges in the graph. Okay? But suppose that all what I have is I have local access to the input, to the graph. So all what I can say is, OK, I can ask a vertex, tell me what is your degree. OK? And I would like to study this question. I would like to make computations. Is this problem easy or difficult? So one can do something in Sublinear-time, as I will show you in a second. Sublinear means better than by checking the degree of every vertex. But actually, this task is not necessarily so simply, as the following very similar problem shows. So suppose that I have n numbers, which in principle could correspond to the degrees in the graph. All of them are, OK, one important thing in the example here, the graph is connected. OK, so this is an important assumption. So now suppose that I have n numbers. All of them are integers between 1 and n minus 1. This can correspond to the degrees of the graph. And I want to estimate the average. This is a very simple problem, very natural problem. Do you know how quickly can we do it? So the answer is you cannot estimate the average in sublinear time. And why this is the case? So I would just give you an example that we cannot get 7 approximation in sublinear-time. So suppose that we have 2 inputs. One consists of all ones, and another has n minus 8 ones, and then 8 numbers are having value n minus 1. Okay? So what is the difference between these 2 inputs? In the first one, the average is 1, and in another one, the average is 7. Okay? But because we have only 8 witnesses showing for these high values, we cannot distinguish between these 2 inputs in sublinear-time. Okay? So this kind of shows you that this problem is not necessarily trivial, and this problem requires linear time. Now, what is the difference between this problem and the problem of the degrees? So there is one nice difference, okay, that we're using the fact the graph is connected. And Uri Feiger showed that one can actually get 2 plus epsilon approximation for n epsilon in time square root of n over epsilon. And how to do it? And why we can do this task. So the main difference between any sequence of integers in the input and the graph is that in the graph, so the reason of a lower bound of root of n for the sequence of integers is that we may have big numbers that are hide nice. But in the graphs, they cannot, because there will be at least one other witness for any vertex that has high degree, because it will be connected to someone. So then, and I will just give you only the result, Uri Feiger showed that just a simple algorithm, randomly sample, repeat 1 over constant number of times, then you randomly sample root of n vertices over some epsilon to some constant, and for each sample, compute the average degree. And then take the smallest of those that you found. And this will be a 2 plus epsilon approximation. Okay? So you see, kind of, in principle, this is a very similar problem to a problem that we know. Yes?
Some quick question. Is this algorithm is deterministic or?
It's randomized.
Randomized?
Yes.
Not deterministic?
Yeah, everything is randomized. So in this talk, everything that I will be talking to you about is randomized. So we randomly sample some big sets of vertices, root of n each, and then we are able to say something. But you see, in principle, very similar problem to the one that we had before, and we have completely different complexity. Now, one can also show that actually root of n over epsilon is necessary here, and no little of n time algorithm can get 2 approximation. So we can get 2 plus epsilon approximation. And to some extent, it was surprising, but Goldreich and Ron improve it by making assumption that if in addition to the information about the degree of every vertex, we can actually also get a neighbor of every vertex, then we can get it much faster, so that you can get 1 plus epsilon approximation also in root of n time. So this is an array, arrow going to the right. So suppose that we have a weighted graph and want to check what is the minimum spanning tree of the graph. Okay? This is another classical problem. And we know that it's well studied. We have linear time randomized algorithm. We don't have linear time deterministic algorithm, but we are almost there. And of course, we cannot beat this running time. But suppose right now that we want to relax the task, and we only want to compute the weight of the minimum spanning tree. And then there is a very nice result, which is kind of able to tell us that by characterizing the weight of minimum spanning tree in the terms of number of connected components of some size, we are able to obtain very good approximation much quicker. And this is kind of easy to observe fact that we know that minimum spanning tree, we can always say, okay, find a graph induced by vertices of length 1, graph induced by vertices of length 1 and 2, and so on and so forth. And you can connect this in some way to obtain a nice formula for the weight of a new spanning tree. And then these bits you can find using some random sampling. So in short, Chazelle, Rubinfeld, Travisan show that we can come up with 1 plus epsilon approximation algorithm running in time dw over epsilon square, where d is the maximum degree, w is the maximum weight, assuming all the weights are between 1 and w. So for example, if you have a graph of maximum degree 20, and all the weights are between 1 and 100, in constant time you can find 1 plus epsilon approximation of the weight, which in my opinion is impressive. Now, I see I was expecting to have more time, but so actually one can extend this result to some extent to graph satisfying triangle inequality. So graph satisfying triangle inequality is a complete graph, so n square edges, where we have triangle inequality, so some like metric. And then in time n poly log, we can find 1 plus epsilon approximation of the minimum spanning tree weight, which is sublinear. Now, I want to give you 2 examples. Again, why sublinear-time is difficult. So there are trivially hard problems. And one of the trivially hard problems is the problem, again in metric graphs, of finding the heaviest edge in the graph. So I have a graph, and I want to find the heaviest edge in the graph. And the graph satisfies, lightest edge in the graph. Okay? And I'm claiming that this task required checking essentially all the edges. And here is an example. Suppose that we have 2 inputs that differ just by 1 edge. So here we have weights n on a complete graph, and here we put 1 on 1 randomly chosen edge. This graph is metric, satisfies triangle inequality, distinguishing between these 2 requires n square time. And the lightest edge will have yes. But suppose now we want to study the heaviest edge, and then the surprising results comes. It's easy. Okay, we can do it in linear time. So the graph has n square edges. We can still do something in linear time. And the idea is very simple. Pick an arbitrary point, arbitrary vertex, find the heaviest edge incident to this vertex, and return it. And by triangle inequality, so this is the whole proof. I'm sorry, but this is times. So this is the whole proof of the result. And this is an apple, which I didn't plan to have an apple. This was QED. Yeah, so this is always a problem of moving to Apple machines. They just like to okay. Then another very nice result, which actually caught me by surprise. We can so suppose we are given a graph of constant degree. Okay? We can in constant time find a size of maximal matching to even the additive error term epsilon n. So you are given some graph and want to check, okay, how many edges will have maximal matching, and in constant time. And this has some implication that, for example, we can estimate the cost of the minimum vertex covered within factor of 2 in constant time, and the size of maximum matching, and so on and so forth. Now, I promised to tell you something about clustering, at least in the abstract. But then I decided, really, the area is at least as important as just one application, which is also important in clustering. So I will just briefly tell you about 2 results. One will be very brief. So several years ago, we have been quite surprised that not many people have been studying the following type of questions. So suppose that I want to find, I have set of points in a space, metric space, and I want to unweight it. So I have distance, metric distance, which tells me how much I have to pay to what is the distance. And I want to solve the standard problems like k-median or k-means. And suppose that I want to study the following simple algorithm. Pick a random sample set of points. On this sample set of points, find an use an algorithm that I have in my package to find a solution for it, and then return clustering, kind of generating by this sample. Surprisingly, not much has been known for this problem. And so, for example, a few years ago, we showed the following type of result, that somehow, if you have alpha approximation, you can come up with an algorithm which will give you 2 alpha plus arbitrary small constant approximation for the problem by having sample size which is, in this case, delta is the diameter of the metric space. But this will be a very quick sublinear-time algorithm. Now, why am I mentioning it? Because many people have been studying this type of algorithms, but people haven't been asking this rigorous question: what is the sample size? Now, I'm running out of time, but I still will try to very briefly tell you the main idea of another clustering algorithm that we have been studying recently. Wanted to study spectral clustering. So we wanted to say, okay, we would like to say that 2 elements are in the 2 points are in the same cluster if they are well connected. They are in distinct clusters if they are separated by something, if they are poorly connected. And in this case, I want to say that the points have high conductance if they are in the same cluster. They have large cut separated by a cut if they are in distinct clusters. So we want to study the problem of checking if a graph is k-clusterable, which means we can separate the set input into k sets such that the graph induced by each set has large conductance and the set has low outer-conductance. Here it means approximately the following. We want to say inside this cluster we have high conductance, and here in the cut we have small conductance. And I will jump a few slides, for example, telling you the definition of the exact definition of this. But this means we have k clusters. This is inner-conductance, outer-conductance. And would like to recognize such cluster structure in sublinear time. So we want to do it in framework of property testing, which is essentially doing the following. We want to distinguish graphs that satisfy this property, are k-clusterable in my language, and are epsilon far from clusterable in my language, which means we need to modify the graph in an epsilon fraction of its edges. And we have the following algorithm, and I won't discuss about this algorithm, but the algorithm is doing the following thing. We randomly sample some number of vertices. We run random walks, many random walks through these vertices. And on the basis of what we see at the end of the random walks, we are saying these vertices will be the same cluster or not. So what does it mean? This, for example, this is our cluster structure. We start random walk here and there, and we see, will they have similar distribution of endpoints? If they will have, we hope that they will we'll just connect them by an edge. In this case, so what we hope that after this algorithm, we'll have kind of set of cliques here and there. And we can show that in time which is proportional to root of n, we can distinguish between such graphs and graphs which are not clusterable. And because it's the end, I want to put the last slide. In my opinion, sublinear algorithms, it's a necessity of time. In computer science, we have been studying, computational complexity algorithms, polynomial time. Even some people will study exponential time algorithms. Nowadays, we have to study something which is much faster. We still don't understand the tools, but I think there is a need that we'll have to see something which will be having some implications. And finally, I will use this word in machine learning too. Thank you.
Thank you.